So let's now talk about dislocation motion. We've talked about force sum dislocations. We derived that, and we distinguish the difference between glide and climb. So we want to look at dislocation glide, which is a stress activated process. So one way we can calculate glide planes is by crossing our basically tangent vector and our Burgers vector. So we can't define a glide plane by definition for a screw. That was going to do cross slip and twinning, but we can do that for an edge dislocation. So we can actually go about trying to, and actually let's go ahead and calculate the normal glide plane for some example type problems. So let's go ahead. We can define our T edge, which we had previously, B edge as well. And to get the normal, I'm just going to cross my T edge, cross my B edge, and I'm going to divide out by the magnitude just to give me a unit vector. But you can see that glide plane, the normal is in the 0, 1, 0 direction. A normal of a plane, or a normal, the normal to that, or the plane where that normal exists, is itself. So my glide plane for that particular example would be 0, 1, 0. So once I calculate the normal, I have my glide plane. It is 0, 1, 0. So you can actually prove that. Actually, you can see that quite kind of straightforward here. So normal, again, leads to my glide plane. Normal and the plane going to have the same notation. We can actually kind of see that right here. So if we draw our typical cube, 1, 2, and 3 directions, if I draw the 0, 1, 0 plane, or if I draw, as we can see here, the normal is going to be, the normal to that plane is in the 0, 1, 0 direction. So again, just a way to kind of see that. Again, there we go. Now we can see our normal direction to that plane. So there are typically going to be systems of glide planes that we encounter. So again, materials always go in the direction of least resistance, or energetically the easiest directions. So if I want to move a dislocation, I want to move along planes that are close packed planes, and I want to move along directions that are close packed directions. Why? Lowest energy, right? It's the minimum energy that I have to move. It's the smallest distance along those close packed planes and along those close packed directions. So we are going to call and define these systems. So for FCC, it's the plane is going to be the 111 planes, the direction 110. BCC doesn't have a close-ist packed plane, but it does have a close-ist packed plane. That would be 110 plane, and then 111 direction will be that value. So for basically these slip systems, those are going to be the ones that are mobile. They are going to be moving, whereas they're going to be glissile, essentially. If they're not in that plane, they are sessile. So they are going to need extra additional energy in order to move. They're going to need to have some climb component, some thermal values as well. We can also describe essentially how much stress is required to move along a glide plane. So we're going to use the Schmidt resolution tensor, alpha ij, to calculate our single value of resolved shear stress. So we need to figure out there's going to be some value inherent to our material. There's a minimum critical resolved shear stress that's going to be required to allow glide to occur. And again, because the dislocation is essentially in that metastable, below is just going to stay there. Above, if you have a resolved shear stress that's greater than your lattice resistance, then basically we're going to move. And they could go through kinks and jogs. They could go out of plane and in plane. So they have a lot of different mechanisms to go through, but that calculating that Schmidt resolution tensor and your critical resolved shear stress, that single value, that's going to be critical to kind of seeing whether your materials move or not. But they can move via kinks and jogs, so that's out of the plane. That does require some thermal activation energy in addition to the stress as well. So there's going to be some velocity to the motion of the kinks that's going to be dependent on the hopping factor, and you see an Arrhenius process yet again appear. And actually, you'll see that this has a very similar form at the end. Again, this is a lot of math, but the key thing you see here, our velocity is going to be proportional to our diffusivity, our tau, our resolved shear stress, over T. That D over T is a very common type phenomenon. We see it as our M factor in kind of nucleation and growth mechanisms, and that goes through, you see that appear quite often in materials. So that's a really, really key parameter that we see in this system. So we can see that occurring here. And again, we see that same velocity if you're kinking or if you're kink or jogs.